All right. So in this question, we need to find the value of A and B for this, for which this equation is satisfied and has four distinct solutions. Okay, keep it in mind. We'll use it further. This information is very crucial. All right. So let's not get confused by the options right now. But by looking at options, we can see that uh, the range of A and B is A. For B, we might not know right now, but for A, it is starting from these things -3, 2, 3, 2. So it may not be of our use directly, but we can always have the options in our mind. Okay, let's start. So firstly, we'll write the equation, what is given to us, and then we'll find what is A and B. We'll find the range, right? Okay, so there might be different ways to solve this algebraically, but we'll use the graphical transformation method because I find it very helpful, and we can do it in very less steps, very few steps, right? Okay, so how to use graphical transformation? I've also previously explained this transformation. You can easily find it. All right. So firstly, we'll look at the function, have a close look at the, not function, the given equation. And for our simplicity, let's write it like fx is equal to gx, where gx is the constant function 2 and fx is this thing. Okay, this thing. All right. So now for plotting fx step by step, firstly we'll see what exactly it is based on. It is based, we can see e raised to the power x somewhere here. So we'll start by that. We'll draw the basic graph of e raised to power x, which we all must know, right? This thing. And x is equal to 0, y is 1, right? All right. So now, after drawing e raised to power x, we can see there is a modulus also. All right. Ignore b for once, but see the focus on the modulus part. So what's the rule of applying a modulus and transforming is that we have to erase all the negative part of the graph, whether it is in negative x-axis or negative y-axis. We have to remove it because modulus cannot allow that, right? All right, and then we'll take the positive part and we'll draw a mirror image of it, right? Okay, so now what is the mirror image of this graph? It is like this, and we have to ensure that this graph is giving positive value for all x and y, right? So this graph is ensuring that initially it was not. So it is pretty simple. We transform this into this. All right. Okay, now we can see a variable b also here. So we have to adjust for that. So whenever we apply the transformation of fx, which is transforming to fx minus b, then we'll shift the graph towards right. Whenever there is a negative term, we have to shift right. And if there is a positive term, we have to shift it left. Since it is negative of b, we'll shift the graph by b units, right? Very simple. Okay, next transformation. We are not done here right now yet. So now we can also see that there is a negative a involved, right? All right, let's focus on this thing. And now for now we are assuming that a belongs to R. Okay, and previously also notice that we are assuming b belongs to R. Right now we're not concerned about the range. We are just assuming for plotting purpose. Okay, so now now we are applying this transformation where fx transform to fx minus some constant a. So whenever we apply an external operator to the function, depending on the operator type, either the function is going to go up in case of positive and down in case of negative sign. So right now we have minus a, so the graph is going to shift downwards by a units, right? So why we have written 1 minus a here? Because initially it was not at origin, remember, it was shifted, right? It was 1 unit above. That's the nature of the graph. Okay, so now after applying this, its peak point is b comma 1 minus a. So after doing every transformation, we need to focus on the peak point every time, right? So that we are easily able to transform. All right, let's move. Are we done yet? No, we are still not done. Yeah, we cannot ignore the external modulus sign, right? So now again the rule of modulus. Can we see some negative part in this? Yes, there is some negative part towards along the y-axis, right? And we cannot afford to have it since we are applying the modulus operator. All right, so what we'll do, we'll convert this thing into positive. We'll take the mirror image towards the x-axis. So in modulus, there is no rule of taking mirror image towards y-axis or x-axis. Previously, we took the mirror image about y-axis according to our need, right? But now we are taking the mirror image about x-axis, right? All right. So now we have transformed this thing finally. So since this it was 1 minus a, and it has we have taken its image, so it will become negative. So it will be a minus 1 right now. Okay, focus on that. We need to keep changing the peak values also. Otherwise, we'll get confused and get wrong answers. All right. So now we'll focus on a condition which was given to us. We need 4 distinct solutions. Remember. All right. So now we'll plot. So now we'll plot fx is equal to gx, right? So gx we already knew initially. It is a constant line, right? But fx was a bit tricky, so we found that. All right. So now we have to find 4 distinct solutions. We have to ensure that. So can we have any case where we can have less than 4 solutions or greater? Greater we cannot see here because the maximum we can see is 1, 2, 3 and 4. But can we see a 3 solution possibility also right here? Yes. Can we also see a 2 solution possibility? But we cannot see this possibility because it is a constant line. This is not going to shift. Remember, what is going to shift is the peak of this graph, right? So the peak can come here in one case, right? Peak can come here. In that case, we'll have 3 solutions. What another case is possible when peak comes even down this line. Then we will have 2 solutions, this and this. But we don't have to do that. We have to ensure that 4 distinct solutions must arise, right? All right. So for 4 distinct solutions, what we must ensure that this peak is always greater than 2, right? It should not even be equal, because if it will be equal, we'll have 3 solutions. Okay. So now we'll put the condition that a minus 1 is greater than 2. Then we'll bring that 1 to the right side. And then finally we'll get the range of a. And did you notice an interesting thing here? That no matter where we put the b, it doesn't matter whether we shift this graph towards left or right. It doesn't matter. B can take anything, even B can go here. No, it cannot go here because it is e raised to power x. Remember, alright? So it cannot go here. But it can go here anywhere. But even if we take negative value of b, we already have a modulus which ensures that everything comes towards the positive x-axis. So we don't need to worry about that. So we notice that wherever we put this p towards x-axis, it does not matter. So we can put any value for b. But we have some restrictions on a here, right? So what is the final answer? Let's come to the conclusion. So the final answer is this, option number C.